today we want to be able to explain the motion of a positively charged particle in an electric field. So first, let's talk about electric fields and what they are. So it's talking about how the field of static electricity, in this case, later we'll talk about different types of electricity, and it's looking at a single positively charged object and its motion in that field. So a field is kind of an arbitrary construct, and we're just talking about, it's a way to kind of visualize how things move around charged objects. An electric field works similarly to gravitational fields, but gravitational fields are always attractive, whereas electric fields can be attractive or repulsive depending on the charge of the objects. So on the left here, you can see Earth's gravitational field. So it always goes in toward the center of the Earth here, whereas and this is similar to an electron. What happens there? An electron, the electric field goes toward the electron as well. An electron's electrical field strength is calculated with the equation E equals the force on the electron divided by Q. So that's how the electric field is calculated. This is in your reference table. Okay, to plot field lines, you have to use a positive test charge. So this is a positive test charge, and you kind of see how that test charge reacts. And again, test charges are always positives. So here we have our positive test charge, and this is an electron. So opposites attract. So that means that the positive test charge goes toward the electron. So the arrow points in the direction the positive charge will travel. So the electric field around an electron is inward. A test charge is dropped into the field to see how it behaves, and like I said, because they attract it, the electric field goes in, and test charges again are always positive. That's the key thing here, is to remember, if you haven't picked up on that. So electric fields, some rules: they go into negative charges and out from positive charges. They always touch the surface of the charge and meet the surface at right angles. More lines or closer lines mean a stronger field, and the lines never touch. Okay, so then here is the proton, and we have our positive charge, and so it moves away because like charges repel. So it goes away from the proton there. So again, an electric field around a positive is outward. So then what happens if there are two charges in the same area? You put a test charge in the area. So around here, this is a positive test charge. It's going to go in. This is a positive test charge here. It's going to go out from here, and you just keep testing as you go around, and you'll see that it goes into the negative and away from the positive, and it goes straight across right here in the middle. So the positive test charge is attracted to the negative charge but repelled by the positive. So that's what the electric field would look like there. But because the field lines are vector quantities and it shows a gradual flow, they are turned gradually rather than going in straight lines. So rather than this kink here, we make it more like a curve. Okay? So then when you have two positive field, there's a couple things that happen. In the center, you have the positive and the positive, and you have a positive test charge here. The two lines meet head on, and they cancel. So they cancel in the middle here. for the two positive charges. And a void is formed, and that's what happens when the electric field, this should be field, is 0. Okay? So then where the lines hit at angles, the resultant field line will be deflected. So you can see that here is the electric field is equal to 0. That's because this, and this meet head on and they equal 0. So like -1 plus a +1 is equal to 0. So they are equal and opposite, and they cancel each other out. And then it means that the rest are deflected away. So then the same thing actually happens with a negative particle, and it's just that the field lines will be reversed. So these are now in, they're in toward the particle instead of away from the particle. Okay, so then we can talk about parallel plates. So at the bottom there is there are the positives, and at the top there are negatives. So then we have it's like a 75% push up here and 25% pull over here, 50 and 50, and then 75 and 25. You can see that you won't ever be tested on the percentages, but just kind of an idea of what happens. The positive particle is pushed away right here, pushed, and then up here it's pulled into the negative plate. Okay, so for the parallel plates, it's curved on the outside, and the electric field inside the parallel plates is always even, so same magnitude. Inside, it's only at the edges where they're kind of a little different there at the edges. So the strength of an electrostatic field is E is equal to the electric force divided by Q, the charge, and it's in newtons per coulomb. The stronger the field, the closer the lines, or more lines.